Hey guys, I was just thinking about some inspirational stories, and I was thinking about my grandma. When she was 60, she started walking 5 miles a day. It's 60. It's amazing. She's 97 now, and we have no idea where she is. None. None. All right, guys, this is topic 11, kinetics. We're going to talk about reaction rates here. And in the first lesson, um, well, we got a little animation here. I should talk about that. So reaction rates, some reactions move quickly, like we see over here. We've got the paper burning, and other reactions happen slower, like rusting of nails, but we still can observe it. But the decomposition of a diamond in our lifetimes, we're not going to notice anything in that. So how fast reactions go, that's the study of kinetics. And so let's get started with this. The first thing we're going to talk about is the collision theory and things that affect our reaction rates. So let's get started here. A reaction rate, what is the rate of reaction? When we observe reactions, we can do it one of two ways. We can watch the rate of the reaction. The rate of reaction is the decrease in the concentration of the reactants, or we can observe the increase in the concentration of products. So like if we were watching paper burn, or a candle burn, by even slower, we can monitor the rate of the reaction by watching the decrease in the wax burning on the candle. As opposed to, with the example before with the nail rusting, we could take a look at the rate of that reaction by the appearance of product, the appearance of the rust appearing here. So here's a reaction that I want you guys to watch, and pay close attention to the timing of it.
Pouring bleach into a beaker of water and blue food dye converts the dye molecules into a colorless form. The timer indicates the progression of the reaction. If we plot the concentration of dye molecules at various times over the course of the reaction, we can determine the rate of the reaction.
So excellent. So we're looking at the decrease in concentration of the reactants, which is the blue food coloring, and we're recording that, or we're comparing that with the speed of the reaction, and that's what rate of reaction is all about. A very important concept in kinetics is called the kinetic theory. The kinetic theory is an explanation on why reactions happen at all. So there's certain things that have to happen in the kinetic theory for a reaction to occur. The first thing is, in order for a reaction to occur, the molecules or atoms must be able to touch each other. If they can't touch each other, they can't react together. But not only do they have to touch each other, they have to hit each other hard enough for the reaction to occur. So if you think about your piece of paper, there's oxygen atoms colliding with the paper right now, and the paper is the fuel, and the oxygen react together to burn up. It's a combustion reaction. But the reason why your paper is not lighting on fire in front of you right now is because they're not hitting each other hard enough. And one way you can do that is by increasing the temperature. Adding a flame to it will spark, can get that to hit each other harder and start this reaction. Another thing that is important for reactions to occur is they have to hit each other with the proper orientation. They have to line up in the right way for the reaction to occur. The different reactants have to collide in a proper orientation for the reaction to occur. Anything that increases these things, the likelihood of collisions, the strengths of the collisions, the orientation of the collisions, anything that can affect these things will increase the speed of the reaction, the rate of the reaction. And that is what we're going to talk about right now, is different things that can affect the rates of reactions. I'm going to first go into this orientation aspect with an actual illustration for you. So this is going to be nitrogen will be blue, red will be oxygen. So this is nitrogen monoxide, which is smog, and smog reacts, or nitrogen monoxide reacts with O3, which is ozone. And when nitrogen monoxide hits ozone, it can have a reaction. But if it doesn't hit hard enough or in the right orientation, the reaction won't occur. You'll just get back the nitrogen monoxide and the ozone. So If this happens, and let's say these two collide together, the collision theory, but they don't collide together in the right orientation, it's enough force, they're hitting strong enough, but not the right orientation, no reaction will occur. However, if you notice the nitrogen monoxide colliding with the ozone in a different orientation than this example here, it's a different orientation, then what can happen is the oxygen from an ozone can attach with the nitrogen monoxide to make nitrogen dioxide. Instead of ozone, this becomes O2. So this is a nice illustration that explains the what I mean about the orientation with the collision theory. Another thing that can affect the rate of reaction is the temperature. Temperature is kinetic energy. As the temperature increases, molecules vibrate faster. So and atoms and ions and everything else. So temperature is the kinetic energy, the vibration of, or the motion of molecules. So if you have a higher temperature, that means that the particles are moving faster. That's exactly what temperature means. So if they're moving faster, they will collide harder and more often. So there'll be more and harder collisions. And if there's more collisions and the collisions are harder, the reaction will go faster. This is going to be a little video, a little lab, where we're going to have a solution of iron 3 chloride added to sodium thiosulfate. The iron 3 chloride is red. That's what makes your blood red. It's this iron. And so you're going to have this solution that's going to be somewhat red, but the double displacement reaction is going to occur, and it will make a clear solution. We've got 3 test tubes, and the 3 test tubes are going to be put in different water baths. The water baths will be 20 degrees Celsius, which is room temperature, 40 degrees Celsius, and 60 degrees Celsius solutions. So we've got these test tubes in 3 different baths. One is 20 degrees Celsius, one's 40, and one is 60. And this reaction is occurring, same concentrations in all of them, the only difference is the temperature. And in the water bath that's warmer, the reaction occurs faster. And the middle one, 40 degrees Celsius, is faster than the 20 degrees Celsius. So this is a nice illustration of how temperature can change the rate of reaction. Another thing that changes the rate of the reaction, I alluded to it in the last video, was concentration. Concentration changes the rate of reaction because if it's more concentrated, there's more opportunity for collisions. So if it's more concentrated, there's more collisions, and the more often things are colliding, the more likely a reaction is to occur. So we're going to do a reaction here, and this is familiar, my students have done this reaction before, where you take magnesium and you place it in hydrochloric acid. We used about a half molar solution of hydrochloric acid, and we caught the hydrogen gas that was released from this. In this reaction, you're going to see a concentration similar to what we did in lab, and a concentration of the hydrochloric acid, which is much more concentrated. It's 6 molar HCl. So let's take a look at the difference of the magnesium reacting in a dilute solution of hydrochloric acid and a concentrated solution of hydrochloric acid.
In the test tubes is hydrochloric acid. On the left is a 0.3 molar solution, and on the right is a 6 molar solution. If we place a strip of magnesium metal in the 0.3 molar solution, the metal begins to react slowly. If we place a similar magnesium strip in the 6 molar solution, the reaction is much more vigorous. Within moments, the reaction is complete. Meanwhile, most of the magnesium in the 0.3 molar solution is still in solid form.
All right, now let's watch another demonstration with concentration. This time I'm going to have some students of mine helping with the demonstration. They're all going to do the same reaction. The difference is the different concentrations of the hydrogen peroxide that I'm going to give them. They don't know which ones they're getting at the start.
Robert, we got to do it all together. Everybody grab and get near your can't see Mr. Rice. Sit back there. Okay, stop it again. Okay, you're going to pour them all in there when we count to 3. And then you're going to set them down and step away. Okay? 1, 2, 3.
Whoa. Oh man, I only want to start.
Okay, it's the same ingredients. We have a higher concentration though in the two of them. We have a very high concentration here. We have 30% hydrogen peroxide. We had a 10% and a 3%.
Oh, the big guy had a 3%.
There we
Okay,
go.
can I stop recording now?
Just
Look like a I would love to do that.
so we can see how the rate of reaction, the speed at which these guys occur, has a lot to do with the actual concentration that we got in there.
Why am I thinking of it?
Because it's only 3%.
Cool. So what we see here is that with different concentrations, the reactions moved at different speeds. So we had a 30% concentration hydrogen peroxide, a 10%, and a 3%. Another thing that can affect the speed of reaction is pressure. Now, pressure can affect speeds of reaction in gases. It doesn't, changing the pressure isn't going to change the speed of reactions in liquids and solids. It's going to change that of gases. And the reason is gases have a lot of empty space between them, where liquids really don't have space between them. They're free to move around, where solids are locked together. So pressure doesn't affect them as much as with gases. So anyways, when you increase pressure, you increase the likelihood of collisions, and that's what makes reactions go faster with pressure. So let's take a look at 3 things that can affect pressure. Maybe think about this right now. What do you know? 3 different things that can affect the pressure of a gas. Let's see if you can go along this journey with us and see if you can figure it out.
If the number of gas molecules in a container is doubled, with no change in the temperature or volume, the number of collisions between gas molecules and the container walls doubles, which translates into a doubling of pressure.
Excellent. So 3 things that can change the pressure of a gas, and the first one is increasing the moles of the gas.
If the temperature of a constant volume of gas is increased, the molecules of the gas move faster, and each collision exerts a greater force on the walls of the container. In addition, because the molecules move faster, the number of collisions between gas molecules and the container walls increases, and therefore so does gas pressure.
And increasing the temperature increases the pressure, again, because the molecules are moving faster, which makes them collide more often with the sides of the container, which increases the pressure. And the third one is decreasing the volume.
If the volume of a container of gas is reduced by half, but the amount of gas remains fixed, more collisions will occur between gas molecules and the container walls in a given time, leading to an increase in the force exerted on those walls.
Cool. So those are the 3 things. In particular, the last one is very special to gases, is changing the volume, because changing the temperature, increasing the temperature, also increases not only does it increase the pressure, but it also increases the kinetic energy. So it's kind of a double whammy for the first 2 with concentration and temperature. But the third one is very unique to gases. The fourth thing we can talk about that will change the reaction rate of is surface area. Molecules can only collide at the surface. Smaller particles have bigger surface area. So they have to touch each other. It's the surface of where things collide that will determine if that determines the reactions. And this is an interesting one that kind of confuses some people, and that is that the smaller particles have a bigger surface area. So if you think about it, if it's a large particle, it looks like there's a lot of surface area. I'll just make this particle like this. It's a large surface area, but a lot of the particle is on the inside that you can't touch it. There's no contact with it. But if you had a little teeny thing, a little teeny particle, then most everything is surface area and there's very little on the inside. So smaller particles have bigger surface area by proportion, is what I mean there. Smaller particles are smaller particles have faster reactions, and the smallest possible molecules or atoms are ions. These are the smallest ones. So the smaller, the faster you go. But even if you're not talking about just the particle size itself, the orientation is important. If you were to take, and my disclaimer, children, do not do this at home. Okay, if you were to take a gas can and you fill it all the way up with gas and you throw a match into it, the surface area that's allowed to combust is just that little hole. And the whole gas tank is, the whole gas can is full of gasoline, but the little hole is a very little bit of a surface area. And what will happen is the match will go, it might make a little fire on top, but more likely it might just hit and burn out. Like nothing happens. You throw a match into a full gas tank, nothing happens. Again, don't do this at home. However, if the gas tank was not completely full, let's say it was half full or even less, then a lot of that area is going to have gas vapor, and those gas particles have a lot of surface area because you have all around the whole particle, and there's a lot of them. If you throw a match into a partially filled gas tank, it will explode. Especially if it was like 10% would be really bad. So the more surface area, the faster the reaction goes. So I've got an example with a liquid gas, and the first one though is going to be with a solid, taking a look how we can change the surface area and change the speed of reaction. So hope you enjoy.
On the plate is a pile of lycopodium powder. If we aim a flame at it, not much happens. If, however, we take some of the lycopodium and then spray it into a flame, the combustion reaction is explosive. The more surface area of the lycopodium particles that is exposed to oxygen, the faster the reaction.
So you can see that in the video here, only the top of the particles are being exposed to the flame, and it does eventually catch fire, but it's only, not even the whole particle is exposed. It's just the top of the particles that are exposed here. But when you spray it in, every particle has exposure to oxygen around it, and the reaction goes quite quickly. And that's the same idea I was talking about with the gas tank.
It's about flammability.
Danger?
What about surface area?
Oh, the more surface area, the faster.
Excellent. The more surface area, the faster the reaction. So, right now, is there a lot of surface area?
No.
So, little surface area, lots of surface area. Speed up this reaction. Isopropyl alcohol goes in here, surface area than it already had. So what I want to do,
Don't burn out, Mr. Rass.
listen closely. I want you guys to listen very closely. You may hear a whoosh. Okay?
Okay, that means shut up.
So listen real close
It's gonna be hard for this class bowl track.
for my whoosh sound, and the bottle will make a nice whoosh. So be quiet and listen.
We're gonna die.
Got it, Karen?
Yeah.
Go. Dang.
And so with this demonstration, I start off in if I was to try to ignite the isopropyl alcohol in the graduated cylinder, the only surface area is the top here and maybe a little bit of vapor in here, and so it would probably just like be a slow burn. But when I put it in a large container, I'm creating a lot of surface area. I spread it around this large container, and now everything's able to react, as opposed to having some things kind of blocked that's not being able to react because it's underneath. Not everything gets to react in the graduated cylinder because a lot of this stuff isn't exposed to the oxygen. It's kind of blocked by the other things. So that's all right, guys. So that is the lesson about the collision theory and different things you can do to change the rate of reaction. If you have any questions, write them down. Let me know next time I see you, and I'd be happy to answer them. Talk to you soon.